All right, here we go with part 2 of 1.3, a little more on limits, and get to introduce you guys to the squeeze theorem. So the first few are really just picking up where we left off in the last video, where you're going to be given functions like this, and you're asked to evaluate the limit as x approaches some value, but the issue we run into is I cannot do direct substitution the way that it's written now. Because you can see as I put this into factored form, if I were to plug in 2, it's going to create a 0 in your denominator. So can't do it the way it's written now. All these, the common theme in all three of these is going to be simplify it first, then you can do direct substitution to get the limit. So limit as x approaches 2, you can see once it's in factored form, these guys would cancel, which means there was a hole in the graph where x equals 2. So once those guys cancel, then I could do direct substitution by plugging in my 2 for x for this guy and for this guy. And when you do that, simplifies nice for us, we get a limit of 2. So one thing we're going to do on this one that you probably haven't done before is we actually rationalize the numerator instead of the denominator. So right here, if I were to plug in, try to do direct substitution by plugging in 4 for x, obviously it's not going to work. That would be undefined at that point. I can't rationalize the denominator because I would still be undefined where x equals 4. So instead we're going to rationalize the numerator. So this is our a minus b on top. So we're going to multiply by a plus b to top and bottom. Remember that when you multiply something by its conjugate, so if this is a minus b and this is a plus b, those come out to be a squared minus b squared. So you shouldn't have to FOIL that if you just kind of remember the formula that we've used so many times in the past. So this is my a squared minus my b squared. On bottom, you will have to do some potentially some distribution to simplify that stuff. So if you look at what we have on this one, if I simplify the top, it would come out to be x minus 4. Well, one of my factors on bottom is also x minus 4, so those guys can cancel, and this is what I would be left with. So you may want to hold off on foiling the bottom until you see what you have that might cancel for you. So if we leave it in factored form, a little easier to see that those things cancel. Now I can do direct substitution by plugging in my 4 for x on bottom. And if you do a little cleanup on that, this is what you would be left with as your limit. And then one other technique that we've used in the past, again, you can see direct substitution right off the bat wouldn't work. Can't plug a 0 into this guy the way it's written now. So instead, I'm going to take the common denominator of x plus 4 and 4, and I'm going to multiply that to the top and to the bottom in order to deal with the complex fraction. So once you distribute this guy all the way through, this is what you come out with. On this one, just did a little cleanup on top, and this is what I was left with. Again, now you see we have something that can cancel. My x's right here can cancel. And so this is what I would be left with once it's completely simplified. Now I can plug in 0 for x and do my direct substitution. So my limit as x approaches 0 from this point would come out to be negative 1 over 16. So common theme on all those. Again, can't use direct substitution if it's undefined. Potentially be able to simplify it and then be able to do direct substitution. If that doesn't work, once you simplify, if you still get a 0 in your denominator, then you have to go back to the other methods, which were you can either make a table, which we did in our previous lesson, or you can look at the graph, which is what we did in our previous lesson as well. So those are kind of your backup methods when direct substitution isn't available. All right, here's how the squeeze theorem works. So this is the second part of this. So all this can be found on page 82 of our chapter 1 handout. And it basically goes something like this. If I have a function that is between two other functions, then the limit of that middle function must also be between the two limits of the two outer functions. So right here they're telling me that f of x is between this function and this function, which means the limit of f of x must also be between this line and this parabola. So all I have to do is take a look at the limit of this guy, and I'll know that the limit of f of x is between those two values. I can give you a little bit maybe better of a calculator view on this. Let me show you the one that I typed in. I tried to zoom in just right so you could sort of see what we're taking a look at here. So this blue line represents the linear function. Right there is 4x minus 9. And the red parabola was this guy. So f of x has to be somewhere between, so if you can see that little space right there, and on down, it's got to stay between those two graphs, and then it can go somewhere into this space right here. Right? So if f of x is between those two functions, then the limit of f of x also has to be between those two functions. So in this particular problem, we are looking at the limit of f of x as x approaches 4. So if I looked at the limit as x approaches 4 of this function, so the limit as x approaches 4 of 4x minus 9, well, this is a good candidate for direct substitution. So I can plug my 4 in right there, and you'll notice that the limit at where x approaches 4 is 7. If I look at the limit as x approaches 4 on the upper function, on the parabola, I can do direct substitution on that one as well. So if I plug in my 4 for x, you'll notice the limit on that one is also 7. So here we run into a case where the limit where x approaches 4 on both of these functions is 7. And since the limit of f of x has to be between those two values, there's only one number it could possibly be. So the limit of f of x as x approaches 4 would also have to be 7, since it has to be between those two functions. So that's our squeeze theorem. Let me give you one more example here, and then we'll call it quits for the day. So again, here's our two functions. So let me show you the two graphs on this one, just to give you a little bit of a visual here. So g of x, we're being told, is a function that is somewhere between f of x and h of x. So I graph those two. So g of x has to be somewhere between the blue and the red, right, all the way through. So I could draw any kind of a graph that goes into this space, hits both those guys where they connect, and then travels anywhere into this space as well, right? So it's got to be between those two functions, which means the limit of g of x also has to be between the limit of those two functions right there. So again, direct substitution is just an easy way to go on this. So ultimately, we are trying to find the limit as x approaches 2 of g of x. We don't even have a function for g of x, so all we know is that it's somewhere between this guy and this guy. Right? So if I were to do direct substitution on my lower function, my f of x, by plugging in that 2 for x, I get a limit of 1. If I do the same thing on my upper function by plugging in 2 for h of x, I also get a limit of 1. So again, I would know that the limit of g of x would also have to be 1, since g of x is between those two functions. So pretty simple on that. Graphs are a good visual for those, but that's all we got for part 2.